hearing you twice.
Yes,
Oh,
yeah,
okay.
that's because of the YouTube stream. Yeah, maybe I can start again. Okay,
Sure.
hello everyone. Katrina Ligett is an associate professor of computer science at the Hebrew University of Jerusalem, where she is also the head of the program on Internet and Society. Her research interests include data privacy, algorithmic fairness, machine learning theory, and algorithmic game theory. She received her PhD in computer science in 2009 from Carnegie Mellon University and did a postdoc at Cornell University. Before joining the Hebrew University, Katrina was on the faculty in computer science and economics at Caltech. And we are very delighted to host your talk. And yes.
Great. Thank you so much. Thank you for this opportunity. I'm honored to be here and pleased to virtually see you all. And thanks for putting together this series. This is really one of the examples of people making lemonade out of lemons. It's been nice to see this crop up as a result of the Corona times. So I'll be talking today about this paper named Gaming Health, Learning from Strategic Interactions in Natural Dynamics. This is work that appeared this year in AI Stats. It's joint with Yoav Bechavod, who's at the Hebrew University of Jerusalem, Stephen Wu, who's now at Carnegie Mellon, and Juba Ziani, who's now at Georgia Tech. Juba is here. I don't know, did Yoav or Stephen also make it? So he has kindly offered to monitor the chat and answer all the hard questions. So you get two authors for the price of one here. Anyway, so let me dive in and tell you the story here. And the story is one that we all know at some point recently. We all sort of realized that, hey, algorithms are making really important decisions about lots of people's lives. And this is happening in the context of things like credit scoring. So algorithms are contributing to decisions about who gets a loan and who doesn't. Algorithms are being used in university admissions. They're being used in bail decision-making. They're being used basically all over the place, also in really tiny decisions that kind of add up to something very significant over time. And people have gotten interested and concerned about this in lots of different ways in recent years. But one of the things that has happened naturally, as there's been more and more awareness of the importance of algorithmic decision-making, is there's been more and more talk, both on the theoretical and sort of academic side of things, but also just sort of the practical day-to-day side of things about, okay, what should I as an individual do? And what does it mean that people are being judged in these ways, and how might they respond, and what is that going to look like? So in particular, in the context of credit scoring, if you go online and you search around, you'll see all sorts of YouTube videos and articles giving people advice on basically how to game the credit scoring system. And it's really interesting because some of this advice actually is sort of legitimate advice endorsed, for example, by the credit scoring agencies. They basically have you play a game in order to understand the game of credit scoring better. And some of this is folks who are at least sort of trying to make it sound like the goal here is sort of to trick the algorithm and get yourself some better credit. But there's a lot of talk about this, and there's naturally a sort of a question that you might have is, okay, as soon as you set high stakes, important objectives, people are going to try to game them. So what's going to happen here? Similarly, algorithms have been used recently in the context of hiring. If you haven't heard about it, if you haven't applied for a job like this, good for you. I'm fortunate to have not been in this position. But basically, algorithms are used in a bunch of different aspects of the hiring process these days. They're used to screen candidate CVs. And so you see advice online about, for example, what keywords you should put in white on your CV so that the algorithm sees them, even if a human won't. Also, when you apply for a job these days, you might be asked to record a sort of video interview in response to questions. So you get a few minutes to record yourself. And so there's all sorts of advice online on how do you game the system. Because the algorithm is going to be, reading this video in the sense of both looking at what your text says and what's the complexity and relevance of the answer, and do you hit on the right keywords, but also potentially is paying attention to things like your vocal variety and the tone that you use and how enthusiastic you seem and the facial expressions in the background potentially all play in. This is actually very controversial, and some of these companies have stepped away from using some of these aspects, at least that's what they say. But there's a lot of questions about, okay, what's going on in this space and what can I do as an individual in order to respond best and sort of have my best chance, given whatever the algorithms are doing. And of course, all of this talk about when you set goals that people will set out to sort of game the metric, when you make those metrics public in particular, that's not new. One form of it has been known for a long time as Goodhart's law. Basically, I'd summarize that as metrics will be gamed. And so, okay, where does that leave us? Well, it leaves us in a really interesting place, apparently, for academic research. There's been a huge amount of interest in recent years to issues related to the fact that we no longer live in the world of machine learning, where we have beautiful, perfect data drawn from some underlying distribution, and all we have to do is learn on those samples. No, now we live in a complicated world in which the data is being generated in response, in some sense, to the classifiers we've been setting, the algorithms we've been picking. And that changes the game potentially very, very significantly. So there are a number of clusters of work that emerged sort of early on in this space. One of them came out of this paper known as Strategic Classification by Hart, Megiddo, Papadimitriou, and Wouters, where the goal was to develop some sort of robustness to gaming. In this study, which is for some of this work, gaming was basically lying to the algorithm. So individuals had the ability to misrepresent to some extent their attributes in response to what they thought would be useful to them. And the goal here is to have the algorithm not sort of be misled too terribly by that. Another cluster of work, which is also sort of in this gaming is bad, gaming is lying about yourself. There's a sort of line of work, and this paper is one example of, okay, we could respond potentially by auditing and sort of checking and punishing people when we catch them lying about their attributes. And so there's a whole cluster of work of this flavor. And of course, all of this has a little bit in sort of common or sort of a similar flavor to the massive body of work these days on adversarial machine learning, where there it's not that somebody's trying to get a good credit score, but maybe they're trying to break your credit scoring algorithm in some way by feeding it weird inputs. So we have all of this concern, though, about all of a sudden our data doesn't come from the distribution that it's supposed to be coming from. What do we make of this? How do we avoid getting ourselves into trouble? If you go and you actually watch some of these terrible, sleazy looking videos about how to game your credit score, some of the advice actually doesn't sound so bad. It says things like, pay down your high interest loans first. Like, that doesn't sound like gaming the system. That actually sounds like a pretty good idea if you want people to become more creditworthy. And so sort of as I started thinking about this context of strategic responses and strategic data in response to these incentives set by these algorithms, I started to get the sense that, maybe actually strategic behavior isn't always such a bad thing. And in particular, strategic behavior where there's sort of a real modification where people aren't lying about their data in response to the algorithm, but they're actually investing in improving themselves in some dimension that's relevant to the task at hand. Maybe that's actually not such a bad thing, right? And so I kind of wandered around for some period of time, talking to anybody who would listen to me. There's this sense of it seems like there's actually maybe a good story to tell about strategic behavior. And this discussion today is one sort of place that we got to with those discussions. So the sense that I had, though, and that we managed to develop into this paper was that maybe there can be sort of actually a self-correcting process going on here. Because if you have a classifier, for example, and if it has certain features that it deems important, then naturally people are going to respond and they're going to invest in those features. And if those features were relevant to the task at hand, well, then great, that sounds like a good outcome. And if the features weren't actually such a good choice, so for example, if your credit scoring algorithm were to have as a factor something that's correlated historically with being good at paying back loans, but actually that has no causal relationship, well, people would realize that perhaps, and maybe they'd find a way to, game the system by investing in performing well on that dimension. But then you would see that that doesn't result in good performance. And then those features would no longer correlate as strongly with good labels. And so future classifiers, if the classifiers were somehow updated over time, would downweight those irrelevant but formerly correlated features. So we give it as an example in the paper. Imagine that some university noticed that students who show up to their interview with their parents in some fancy car actually tend to do well in university. Probably that's not causally related, but you could imagine that showing up in a fancy car is correlated with having had all sorts of privileges and opportunities in life that maybe would allow you to perform well in university. And so, but suppose they didn't think it through and they just included having a fancy car as an important factor in admissions and then published that fact. Well, maybe what would happen is students of lesser means would nonetheless invest in renting a fancy car for one day, would show up for the interviews, get into the university, but perhaps we would discover over time that correlation was not so interesting. Maybe that correlation would be broken and the university would have to rethink its admission strategy. The idea is that somehow there should be some cycle of learning between the learner and the agents, where the learner publishes a public classifier, the agents make strategic modifications, meaning they actually invest in improving themselves, not lying about themselves, but they actually invest in improving themselves in response to this classifier and whatever it prioritizes. And that somehow should generate some useful information for the learner. And that should allow the learner over time to actually improve the quality of the classifier. So that's the idea that we had. So formally, how do we go about showing some version of this story? And I should say up front, this is not really a talk about this particular model. This is a model that we, in some sense, use to illustrate this story, to show, yes, the story can happen. And I think that the story itself is interesting. And I think that the model is nice, but I'm not making any claim that this is a good model of something that's actually happening in the real world. So feel free to complain about the details of the model. I don't think that's really the central thing here, though. And basically my plan is I'm going to walk you through how we come up with this model that tells this story that I was getting at. And then at the end, I'm going to try to give you a little bit of a sample of a bunch of the other stuff that's going on in sort of strategic classification space, to give you a sense that, this is one corner of the story, but I think there's a lot of richness to this space. And at the end, I'll hint a bit towards additional questions that I think are worth looking into. Okay, so what's the model that we work with? We work with a model where each of the agents has some feature vector, and there's some universal true latent regression parameters. There's some true beta star. And so if an agent shows up with a particular X as their feature vector, then their label is obtained exactly as you might expect. We hit that feature vector with a beta star, and then there's some additional random noise. And we assume that there's some bound to the random noise and it's zero-centered. And that's how you get a true label. And then the model we have is one where we assume that there's some underlying distribution over those feature vectors. And there's some covariance matrix, which would be important for the details of the results if I dug deeply into the details, but I'm really not going to. I'm going to hide a lot of sort of parameters when I state the flavor of the results. But the important thing to realize is that covariance matrix may not be full rank. We make an assumption that distribution of the vectors that people are born with, in some sense, is zero mean. I think that's a fine assumption to make. Among other things, if you lived in a world in which that wasn't true, one thing you could do as a learner is you could just hang around for a while watching people's vectors until you learned what's the average, vector that people are born with, without interfering with the world in any way. And then you could just subtract that from the vectors that you see in the future. So I think that's pretty benign. And then, so we have this model with an interaction. So we have a learner who's going to periodically post some beta hat as a regression parameters. And then we have agents who subsequently arrive. They observe that beta hat and they're born, each of them, with some true vector of parameters, x. But then they have some opportunity, and I'll tell you in a slide what I mean by this precisely. They have some opportunity to modify that x that they're born with into some x bar. So that's an x bar that is going to be chosen specifically in response to the beta hat that's been posted to sort of improve how they get classified or sort of how they get labeled by the regression. And then the learner observes what? The learner observes the labels or the sort of the Y bars of these people who show up. But notice, because this was a true investment, when somebody was born with an X and sort of put in some effort to change themselves into an X bar, because that was a true investment, the X bar is actually the thing that determines the Y bar, not the original X. Okay, so what are the rules for how you get to modify yourself? You don't get to just sort of change yourself into any other alternative person you could have been born as, but instead, we assume that there's this very simple model where you're born with this X, and then you have some cost of modifying each of your features, and you have some budget for investing in modifications. And we assume that those costs in that budget are drawn for some distribution that's unknown to the learner. The sort of properties of that distribution, if we dug into it, would be important for sort of the final parameters that would show up in the result. But we're going to sort of treat all of the things that come out of that as sort of constants to not pay too much attention to. But you'll see as we go along, what you might worry about in these distributions that would make it harder to get these positive results. But so what we really need is just that there's some cost to modifications, and you have some budget to modify. And so each individual who shows up might have different costs for each of the particular entries in the vector, and each of the entries may be weighted differently for each person. But basically, because we've set it this way, what agents do is they show up with their X, they know what the beta hat is that they're optimizing against, and so they're going to pick some allocation of their budget in order to maximize their performance. And because we've set it up this way, it turns out what an agent could do optimally is to fully invest in a single feature that basically maximizes their bang for buck. So you look at the features and maximize this ratio between sort of how emphasized they are by our linear regression divided by how expensive they are to invest in. So again, very, very simple model. You could think about sort of more sophisticated things, but the idea is that people are going to show up and they're going to say, oh, wow, okay, this is where I ought to spend my budget. This is where it's really worthwhile. I have a deficit here and it matters, and it's not that expensive to invest here. I'm going to go for it. And really, we didn't need exactly this model in order to get these results. We don't really need this sort of linearity of the costs. We just basically need something that results in the agents not modifying their features in some way that's like perfectly correlated, because this modification is going to have to give us some information, which will make more sense in a couple of slides. Okay, so back to this. So basically, again, beta hats get posted, people show up, modify their vectors in response to the beta hats, learners get to observe the Ys. Okay, so how should a learner in this kind of a situation behave? A learner who knows that people are showing up and they're strategically modifying themselves. Well, I guess it depends what the learner wants to do, but suppose the learner actually wants to classify people well. One thing a learner could do, if it knew it were in this situation, is it could intentionally explore in the following sense. It could basically post a model that focuses on feature one for a while, sort of focus on learning what's going on there in the true underlying beta, then focus on feature two, and so on and so forth, and could eventually learn that beta star. But it's not super interesting or super realistic. I mean, this basically says, hey, give out loans at random for a long period of time, and eventually you'll learn, how to do it right. Most people aren't willing to do that in their high stakes situations. But perhaps more natural would be to say, the learner's going to do the best that it can with the information that it has so far. So the learner is initially going to post some beta hat, and then it's going to see a bunch of data, a bunch of X bar, Y bars, and then it's going to periodically retrain its model. And when it's retraining at a particular time tau, what it's going to do is it's going to pick a new beta hat. It's going to pick a new beta hat that basically optimizes with respect to all the data it's seen so far. So it's going to sort of minimize the square difference. The sum of the square differences. So, and then we'll allow our learners to, or our learner, singular, to retrain every n steps for some n that it gets to pick. The idea is, okay, periodically you look at your data and you say, hey, what should I do? People are behaving, differently perhaps than they were in the past. Over time I should adapt to that. Again, very simple. Okay, so now we have a model that kind of looks like that picture we were saying before. So we have this interaction between the learner and the n agents. Beta hats get posted in response to a particular beta hat. There's sort of the sequence of X bar, Y bars that gets generated, and the learner is going to optimize in response and pick a new beta hat. Questions about the model before we continue on? Questions? I'm not watching the chat. I apologize. Anything from the chat that I should pull up? Okay, I'll forge ahead if it doesn't seem like there's anything so far that needs attention. But do feel free to ask questions. Okay, so what would we want to be able to say about the setting, with this interaction between the strategic agents and the learner, where we have this sort of cycle of interactions? Well, we might want to be able to say something along the lines of, hey, even if some features were correlated with good labels in the underlying distribution, according to the underlying distribution, if they weren't really, and I say this with great trepidation, causally related to good performance in the Y, maybe somehow we would want the learner to figure this out. So in particular, if a feature actually doesn't, by way of the beta hat, actually impact your performance at all, if it's just a 0 in the beta hat, then it's not really an important feature. It's not really a meaningful feature. It may be perfectly correlated with some other meaningful feature, but wouldn't it be cool if the learner could somehow start to tease apart these causal and non-causal, or meaningful and non-meaningful features? So I use the word causal with great hesitation and trepidation for a number of reasons, but one of them is just that our model here is super, super simple. And usually when people talk about causality, they talk about it in a setting where there's sort of much more sophistication and sort of relationships between the various variables. And we live right now today in this very, very simple world in this model where we can intervene on a single variable and that doesn't have any impact on any of the other variables. So if I invest in, becoming a better violinist, that doesn't make me also a better pianist, or any of my other variables. They just don't change. And because it's very, very limited, I'll try not to use the word causality, but you should sort of have it in the back of your mind because it is relevant to the story here. And so the idea is that somehow we have a challenge for our learner, because regardless of whether features are meaningful, they might be correlated in the underlying distribution. And so somehow the learner is going to have to naturally break apart those correlations in order to understand what is meaningful and what is not meaningful. Okay. So that's a hint at this question, the answer to this question, which is, so why is it going to be useful to a learner that she's getting strategically modified observations? We said at the beginning of the talk, people are really worried about strategic modification. Why is it actually going to be good news? So let's understand why not getting modified observations is not going to allow the learner to do much. It's perhaps not super surprising. So the example is just a really simple one. Each individual has two variables that describe her, and our underlying beta star is 1, 0. So the first variable matters, the second variable doesn't. But let's assume we live in a world in which that second feature is actually correlated with the first one perfectly in the distribution of unmodified features with which people are born. So there's initial X's that people are born with. So if those two features are always perfectly correlated in the underlying data, then any regression parameter, it's going to look okay. I mean, it's going to be indistinguishable from this beta star, right? And so you have no hope of making progress if you have these correlations and you don't have some way to break them. So the hope is that this interaction is going to let us break them. And notice, if you were in this situation with these perfectly correlated features, that if a learner picked a really bad beta star, beta hat, picked something that really emphasized the second feature instead of the first feature, and the agents responded to it, then the learner would notice the bad beta hat because this correlation would get broken. Okay, so great. I mean, it sounds really promising. Correlations are going to get broken. Everything's going to be fine. Problem solved, right? So the question is, is it really? So what happens? Does the learner over time necessarily recover the true beta star just by sort of this very simple natural interaction with these strategic agents? And okay, well, not necessarily. So why not? So the concern is this. The concern is that if the agents actually never invest in a manner that differentiates between two particular correlated features, then the learner can't tell which of them is meaningful. And we haven't said anything yet to convince ourselves that the agents are necessarily going to be incentivized to invest in all the right ways in order to sort of disambiguate all the features that we need to in order to understand what's really going on. Okay, so the structure of our approach, sort of the structure of the proof, is going to have basically two parts. The first part of this is one where we focus on giving a guarantee that only holds with respect to the features that actually get modified by the agents through this interaction. And then the second part is to say, oh, actually, we can tell a story about this learner such that this dynamic interaction actually shapes a set of modified features in a useful way. So we actually end up together being able to say something quite general and quite, I think, nice. Okay, so let's focus first on this first part, which is just, okay, let's not worry about which features get modified, but suppose some of them get modified in response to, the stated beta hats. Can we say something nice about those features? Okay. So the idea that we need here is we need that those manipulated X's, so the ones after people invest in changes, are full rank in the subspace that's defined by the features that have been manipulated so far. And the issue is that if there are very, very strong correlations in our observations of the features, then we have a small minimum eigenvalue of the observation matrix, sort of a matrix of those observed X bars. And that unavoidably, it's not just a sort of weakness of the algorithm, that unavoidably makes recovery of the underlying beta star harder. And so sort of through this argument, the correlation between the modifications across the features becomes a parameter that actually affects the recovery guarantees. This is not something I'm going to dig into, but I kind of want to point to it so you can sort of see how this would sort of naturally be something that would matter. And so in sort of the theorem that comes out for this piece of the argument, initially this isn't going to be impossible to read, but hopefully I'll make it something that you can read in just a second. It says the following. Okay, well, let's put some sort of notation on here to try to understand what all these pieces mean. It says that basically at all points in time, if you look at any point at which the learner is updated her stated beta, what can we say? Well, we can say with high probability that if we have enough samples per epoch, so we have enough observations in between the times in which she changed her beta, then we can give a guarantee, that's the second line, that says that, well, if we just focus on the features that have actually been manipulated up to that point in time, and we look at our performance, meaning sort of our recovery of the beta star, on just those features, that actually that we can say some nice guarantee about that. Okay, this is still a little hard to interpret. So maybe first I'll point to, like, there's a bunch of stuff hidden here. So I'm hiding constants that depend on the modification costs and the budgets, on that bound that I assumed, on the noise, and sort of, I'm hiding lots of details here. I'm just trying to give some intuition. One piece of interpretation for this statement is, well, let's focus first on the case where we have basically some very small number of epochs. So the beta doesn't get changed very often. And the point here is that if the beta doesn't get changed very often, then essentially we're not getting this benefit of the interaction. We're getting very little of it. We're getting very little of this sort of feedback loop that we were hoping was going to drive something cool. And instead, we're in a situation in which not very many things get modified strategically, and we're basically kind of seeing the original data. And so it's not surprising that the results kind of revert back to the recovery guarantees that you can get for least squares regression for a single batch. Sort of IID observations from the sort of the list of features. So, okay, not surprising. More interesting is, okay, when the epoch size is smaller and therefore there are more opportunities for the learner to update her beta, okay, good things happen because more features get modified. But there's a trade-off here. Because some features are only going to be modified in some epochs, and you see some sort of accuracy degradation when we're sort of in this regime. Okay, but maybe there's something we can do with this, and the hope is that we're going to be able to sort of get the trade-offs right and combine this with some sort of statement about how many features actually get explored, sort of get modified. Due to the interaction with the learner, and hopefully we'll be able to put this together into something nice. Okay. All right, so back to the sort of form of the argument. So that was the first piece where we focus on giving guarantee only for the features that actually get modified. The second part of this is exactly, okay, now let's say something is actually going to get modified, preferably lots of things. Okay, so how can we make an argument about this? So the challenge here is, we want somehow to have a diverse set of features that gets modified. Okay, so what is it that's causing some features to get modified or not? So remember, what's the problem that the learner is solving? So the learner is solving this least square regression problem. Basically, she's looking historically at the X bars and Y bars she's seen, and she's picking a beta to sort of respond well to that. Okay, so one way you could sort of rewrite this problem that the learner is solving then is you could say, okay, I'm going to write a big X bar for my sort of matrix of X bar observations, these modified feature vectors. I could write Y bar for the corresponding matrix of observed labels. And so the learner is solving sort of this alternate formulation of the problem. And the thing to observe here is that if those modified features, if that modified feature matrix has basically sort of explored in all of the directions, so if you have an invertible matrix here, then there's a single solution to this optimization problem for the learner. And it's obvious in some sense, what beta should she pick? But if we haven't pushed in all the directions yet, we have this rank deficient matrix of observations, you could have a continuum of possible optimal solutions for the learner. And so there's a question, which is also an opportunity, this question of how should the learner tie break? And so this is an opportunity that we seize in order to try to pick a tie-breaking rule that is going to help us with our goal of getting some sort of nice properties of this interaction. Okay, so what could you do? One idea is that the learner could just pick the minimum norm solution to that least squares problem. And that's a very natural thing to do. It's the kind of thing that I think comes to mind first. And let's sort of think a little bit about what might go wrong with that idea. So let's do an example. So again, let's live in a world in which each person only has two variables associated with them. And in this example, let's do it with a beta star that has 1, 2. So both of those features matter for your performance, but the second one matters more. Okay. Again, let's have no noise. So the epsilon is 0. And let's live in a world in which actually all of the sort of individuals, all of the agents are born with a vector of 0, 0. Everybody has a budget of 1, so everybody gets 1 unit of money to spend on modifications. And the costs of modifying in both of the vectors for all of the agents are 1. So you're sort of indifferent there on your modification. And suppose that the initial regression parameter that the learner picked just happened to emphasize the first parameter more than the second parameter. Okay, could happen. She had no information when she picked it. So then what are the agents going to do in response? They're going to show up. They're all born as a 0, 0, and they're going to try to figure out how to respond, how to sort of invest in response to something that is prioritizing the first piece of their vector. So naturally, they're all going to invest fully in that first entry. And that's going to induce observations that are the x bars of 1, 0. What are the true labels of those 1, 0 people going to be? Well, they're going to be y bars of 1. So then we see a bunch of these agents show up over and over and over again with this x bar and this y bar. And then the learner steps back and says, okay, so I get to modify my beta. Now what should I do? Well, she has choices, right? Because she actually doesn't know anything about the second variable. So there are a bunch of optimal solutions to the problem that she faces, but the minimum norm solution is a beta hat of 1, 0. And so now our learner is stuck because, oh wait, she's back where she started. What are people going to do in response to this? They're going to invest in the first variable, and she's never going to induce these agents to modify the second variable. She's never going to learn that actually, oops, she should have been paying attention to that because that was actually more important for performance. Okay, so focusing in on this sort of minimum norm solution gets us stuck in a corner. So maybe we can do something else. What if we could somehow emphasize solutions that have larger norm? And the idea is that we use is the following. So basically, if we're in one of these situations where there are unexplored parameters, then what the learner can do is she can start out with the minimal norm beta that solves her least squares problem, and then she can kind of shift it. And she can shift it so it's still an optimal solution, but she can shift it sort of adding some weight according to the directions in which there hasn't been observed manipulation, observed modification in the x bar so far. And basically she can do this in a way that ensures that some unexplored feature is going to get somewhat substantial weight, which is going to encourage the agents to invest in that direction. Of course, you can't force them to invest in that direction, sort of no matter how sort of hard she pushes, because maybe they're going to show up with cost functions that make it sort of undesirable to invest in that direction. So obviously, there's going to be a role for the budgets and the cost functions in the final result. And there's sort of a trade-off here, sort of how much of her weight she puts into encouraging this kind of exploration on the part of the agents. And so that's something that we need to work out and balance in the final statement. But what we managed to do is we managed to basically take the first statement, combine it with this algorithm that encourages this tie breaking to get a final overall recovery theorem that says if we have sort of enough samples per epoch, then there's a way for the agent to pick that sort of weight, that incentive to explore that she places in her choice of the beta, such that after a certain point in time, and a kind of reasonable point in time, then with high probability, the beta hat that she's going to be picking at that after that time actually is doing recovery in like the real sense, like the beta hat is getting to be close to the beta star. All right, so this is a little hard to interpret right now because there are various things that depend on each other. So we can kind of rewrite this to give a little bit more interpretation. So this is saying, like, when we get substantially past the point where the number of observations is equal to the number of dimensions. Clearly, we need to get past that point if we're going to make any progress on this problem. So that's not too surprising. Then the optimal recovery rate is going to be achieved for epoch sizes that look something like T over D. So that we're spending some of our time in each of the epochs, but not all of our time there. And that if you set the parameters right, then you get a final bound of this O of D root D log D over T for this L2 recovery guarantees. And so this is kind of nice. This is sort of a statement that says, yeah, actually, there is a way to set the incentives for the agents that comes very naturally, I think, or pretty naturally on the part of the learner that makes that strategic aspect of the agents actually beneficial. And it's beneficial not just for them in that, they can, use their budgets in order to sort of perform better, but it also has sort of a nice system-wide impact in that the learner gets pushed over time to a better and better classifier, and better in sort of just the right sense. Over time, that classifier manages to tease out which of the variables were just correlated in the underlying distribution and which of them were actually causal or meaningful. And also, as sort of a side effect of this, over time, the incentives set by the learner in posting that classifier publicly actually push the agents sort of as a whole, as a body, to invest more and more in the meaningful variables. So people over time spend less of their money and their effort on renting fancy cars to show up to admissions interviews, and more of their time and their effort on studying for their courses and studying for exams that will help them, perform better in university and so on and so forth. And so you have this sort of positive effects for individuals and for society and for the learner sort of all around in this story. Okay, so I promised you I was going to spend a few minutes stepping back and like sampling in some sense the landscape of what's going on in strategic regression, strategic classification, strategic response to learning space. There's a ton going on. I am not going to give a proper summary of everything. I'm not even going to cover every paper that's been written in the past year, but I'm going to try to give you a sense of what's going on in the space because there's a lot. I think it's very interesting. So one paper that I wanted to point to is this paper, Strategic Classification is Causal Modeling in Disguise. So we are not the first or the only ones to feel like there's something related to causality going on in the space of strategic classification. And in particular, what this paper does is it highlights a deep and nice connection in a particular model of the problem that says that if you want to design classifiers that are going to incentivize agents to improve on the right variables, the actually relevant variables for the task at hand, then in their formulation of the problem, this requires solving a potentially hard causal inference problem. And in some sense, this is not surprising. If you want to induce people to actually invest in the right variables, you have to understand what the right variables are. You actually really have to deeply understand the mechanism that's generating those Y's or the observations in your space, the true labels. So, but it's very nice that it makes this very sort of formal and concrete. Another sort of take on causality in this space is this paper of Stephen and collaborators that in some sense builds on the work that I presented today. They use a slightly different model, but the observation that they have is, in some sense, you can use this sort of sequence of classifiers, so these different betas in our language that get posted by the learner as instrumental variables. So this is sort of like almost like a natural experiment, sort of natural variation that allow you to uncover the underlying causal relationships between observable features and outcomes. And so they actually take the causality thing a little bit sort of more deeply and more seriously than we do in the work that I've presented today. And I think that's quite nice and quite satisfying. There's been another sort of whole collection of papers that try to understand, this is sort of a game theoretic question. One of the notions that comes out in this space is that of performative stability. That's from this paper, Performative Prediction. And the idea of performative stability is that you're interested in when a classifier performs well, not on the sort of underlying data distribution that people are born with, but on the data distribution that it induces once people respond to the incentives set by the classifier. That's sort of an interesting property for a classifier to have and a desirable property for a classifier to have, because people are really going to respond. What you care about is its performance not on some imaginary distribution that doesn't exist anymore, but in the distribution you're actually going to have at hand. And so in the model that they study, they managed to give necessary and sufficient conditions for a classifier to have this property. A lot of the work in this space, I think, has been influenced by this paper of Kleinberg and Raghavan, where there's this focus on how we've got this game between a learner and agents, and how can we somehow design the assessment rules that can incentivize those agents to invest in the meaningful improvements. And they give some characterization there. And people have taken this in a bunch of different directions. This paper on stateful strategic regression takes it in the direction of sort of enriching the interaction between the learner and the agent, so that there can be multiple rounds of interactions with a particular agent, unlike our model where, you know, people show up once, they present themselves once, and they get classified, and then we never see them again. When you have a richer interaction, some interesting things can happen. And sort of also in this framing of sort of this game as sort of a Stackelberg strategy game, the traditional framing is one in which sort of the classifier goes first, the learner goes first. They post their classifier and the agents respond. So they modify themselves to respond. This paper of Zernick et al. Asks the question, okay, what if we flip things on their heads and we have the agents lead? And they give some stories for why, actually, for some of the strategic classification scenarios that you might actually really care about, this is actually not a crazy version of the story to look at. And they show that can change the game, and it can change. You can get different equilibria in the resulting game. And also there's been some critique of sort of this game as framed, and some sort of lack of robustness, some instability that you can see in it as it's been sort of commonly framed. And this paper gives sort of an alternative, sort of more robust way of framing this interaction game. And also, so all this work so far that I was talking about has this idea that people are going to respond to a classifier that's been posted for them, actually most of the work. But also it's natural to ask the question, okay, people can potentially respond to a classifier even if they don't know what the classifier is entirely, because they can learn something about the classifier over time from their interactions, from the interactions that they see others have with that classifier. And so things about classifiers are revealed over time through these interactions. And that's something you really actually see in the real world, where, you know, people are trying to figure out what are the factors that matter when they're faced with these algorithms that are making important decisions about them. And they're trying to learn from their previous experience, from the experience of others. People are trying to sort of gather their data together in various groups in order to try to get some more transparency there. This paper asks questions of this flavor, sort of, when does transparency actually improve prediction error? When does it not? This particular paper, I think, is in the framing of strategic behavior being lying about your characteristics, but you can sort of take these ideas also to the model where strategic behavior is actually sort of real change in response to incentives. Okay, so as I suggested, there's a lot going on in this space. I didn't even manage to survey all of it. What's next? I think there's actually, despite the fact that there's a lot going on, there's a lot that still can be done. One idea would be to try to sort of give some more sort of comprehensive universal framing around these various models of the strategic behavior of the agent. So we have, versions where agents are lying, versions where agents are sort of optimally responding to the incentives that have been set for them. There's also all this, adversarial machine learning where agents are just doing whatever's going to, hurt the learner as much as possible. Is there anything we can do to sort of put some structure around all of these different models and say something a little bit at a higher level? Another thing that I was just thinking about recently is I've never quite been able to make sense of explainability to myself. And I wonder if maybe there's an opportunity to say something about the role of explainable classifiers as sort of, partial disclosure about the classifiers that could incentivize good investment, sort of to play in the space of maybe you don't post the classifiers, you post information that's, useful and interpretable on the part of agents, and that you can use that to sort of shape good investment and, get good sort of results of dynamics. When we set out to write something or do something in this space, I think we all thought we were going to write a paper about fairness. And that somehow didn't happen because there was enough else to think about on the way. And we didn't quite get to the fairness. But I still think that it's important to step back a bit and say, okay, hold on. These are decisions that are being made about real people. And they're incredibly influential, not just for the lives of those individual people, but sort of for the fabric of society. What do we want from this decision making? And are there important issues raised by specifically strategic behavior in response to classifiers? So versions of this question are things like, what if individuals or groups of people have uneven access to information about the true classifier? Maybe they have different past data on how it's behaved. Maybe they have different ability to adapt to it. Maybe even if they have some information about the classifier, that could potentially result in unfairness, not just for the current generation, but you can imagine some sort of story that would involve some feedback that could potentially really create sort of divergent, unfair outcomes across populations. And I think there's also room to do sort of some more work that explores this link to causality that I alluded to briefly, because clearly there's something really interesting going on in this sort of two-sided adaptivity that seems to get you something that you can't get if only one or the other of the sides is sort of adapting and learning. And it seems to expose something really important about sort of the underlying mechanics of the situation. I think it's maybe worth trying to dig into that deeper. All right, I will stop there. And thank you. Be happy to take questions.
Thank you very much, Katrina. Are there any questions? Yeah, if you want, you can just unmute yourself and ask the question.
I suspect Juba answered all the questions in the chat. I wasn't watching the chat. Thank you. That's
Hi,
awesome.
Katrina.
I only had 2 questions to answer. That's fine.
Oh, okay. All right.
Hey, Katrina. Thanks for a great talk. Really enjoyed it.
Thanks.
I have a question regarding this. Let me try. So I was going to ask, so when you choose to update a beta, so you're directly just solving the mean square and then maybe break ties using the least norm. So it sounds like you want to have some diversity in the beta you choose so that people would try to, explore different features. Mm-hmm. So would it be possible just to add something like a negative entropy regularizar, and would that sort of, have a similar effect on the performance?
It's a good question. Yeah. So you basically need to make sure that you're going to push in some directions that you haven't explored in some way that's not going to harm your classifier too much. I don't think we looked at that explicitly. Jim, feel free to correct me if I'm wrong, but it sounds like it could plausibly also do the trick.
We didn't look at that explicitly. Oh, sorry.
Yeah, go for it. Yeah.
We didn't look at that explicitly, but like just the idea is really you want to induce some, possibly small, but you want to induce some small probability of manipulation in direction I haven't seen so far. So there are possibly like many different ways to do this. Kind of like the tiebreaking we're looking at in the specific paper is just like one possible rule. But I imagine that like also like it depends on the assumptions in the cost function. Like for a reasonable cost function, if you kind of like have the right regularizer, so like something about entropy right now, it pushes you to put some weights, like some non-zero weights in directions they haven't explored, then with some probability, the cost function is going to be such that it's going to be good for you to pick that direction, and then you're going to start learning in that direction. So yeah, I think you can do something in those lines.
Okay.
Yeah.
Thanks.
Yeah, thanks for the question.
Thank you again, Katrina. I believe we are just on time, and
Okay.
thank you all. Bye-bye.
Great. Thanks again. Take care, everybody.
Thanks.
Thank you, Katrina.